Hello everyone. In today's video, we are going to learn about Q-learning algorithm. Introduction. In reinforcement learning, we have an environment that we want to learn. For doing that, we build an agent who will interact with the environment through a trial error process. At each time, step t, the agent is at a certain state s underscore t and chooses an action a underscore t to perform. The environment runs the selected action and returns a reward to the agent. The higher is the reward, the better is the action. The environment also tells the agent whether he is done or not. So, an episode can be represented as a sequence of state, action, reward. The goal of the agent is to maximize the total rewards he will get from the environment. The function to maximize is called the expected discounted return function that we denote as G. The equation is represented here. To do so, the agent needs to find an optimal policy pi, which is a probability distribution of a given state over actions. Under the optimal policy, the Bellman optimality equation is satisfied, which is represented here, where Q is the action value function or Q value function. All these functions are explained prior. Q-learning algorithm. In the Q-learning algorithm, the goal is to learn iteratively the optimal Q-value function using the Bellman optimality equation. To do so, we store all the Q values in a table that we will update at each time step using the Q-learning iteration, which is represented here, where alpha is the learning rate, an important hyperparameter that we need to tune since it controls the convergence. Now we would start implementing the Q-learning algorithm, but we need to talk about the exploration exploitation trade off. But why? In the beginning, the agent has no idea about the environment. He is more likely to explore new things than to exploit his knowledge because he has no knowledge. So, through time steps, the agent will get more and more information about how the environment works, and then he is more likely to exploit his knowledge than exploring new things. If we skip this important step, the Q value function will converge to a local minimum, which in most of the time is far from the optimal Q value function. To handle this, we will have a threshold which will decay every episode using exponential decay formula. By doing that, at every time step t, we will sample a variable uniformly over 0, comma 1. If the variable is smaller than the threshold, the agent will explore the environment, otherwise, he will exploit his knowledge. The exponential decay formula is represented here, where n underscore 0 is the initial value and gamma, a constant called a decay constant. The graph is an example of the exponential decay. Here we will use the frozen lake environment of the GIM Python library, which provides many environments including Atari games and Cartpole. Frozen lake environment consists of a 4 by 4 grid representing a surface. The agent always starts from the state 0, 0, comma 0 in the grid, and his goal is to reach the state 16, 4, comma 4 in the grid. On his way, he could find some frozen surfaces or fall in a hole. If he falls, the episode is ended when the agent reaches the goal. The reward is equal to 1, otherwise, it is equal to 0. Q-learning algorithm implementation. First, we import the needed libraries, NumPy for accessing and updating the Q table, and Gin to use the frozen lake environment. Then, we initiate our environment and get its sizes. We need to create and initialize the Q table to 0. The code is represented for that, and this is the output that is obtained. We define the different parameters and hyperparameters we talked about in this post. This is the code to evaluate the agent training. We will store the total rewards he gets from the environment after each episode in a list that we will use after the training is finished. This code has to be executed. Now, let's go to the main loop where all the process will happen. This is the code to be implemented. Once our agent is trained, we will test his performance using the rewards per episode list. We will do that by evaluating his performance every 1,000 episodes. So, this is the code to be implemented, and this is the output that will be obtained after the code is implemented. As we can notice, the performance of the agent is very bad in the beginning, but he improved his efficiency through training. Q-learning algorithm is a very efficient way for an agent to learn how the environment works. Otherwise, in the case where the state space, the action space, or both of them are continuous, it would be impossible to store all the Q values because it would need a huge amount of memory. The agent would also need many more episodes to learn about the environment. As a solution, we can use a deep neural network to approximate the Q value function. Since DNNs are known for their efficiency to approximate functions, we talk about deep Q networks, and this will be the topic next. In conclusion, mastering optimal decision making through Q learning is an ongoing journey. Embracing the principles, addressing the challenges, and staying updated with advancements are essential for leveraging Q learning effectively in diverse decision making scenarios. Thank you.